we are now on to the second part of our series on charge, voltage, and current. My name is Vivek Subramanian.
And I'm Michelle Maharvitz. Let's get started. Let's talk about voltage. So consider 2 points in space. Here we have point A and point B. In most of this class, these points will be points on your circuit, but they could just as easily be 2 arbitrary points out in space. So we're going to define voltage or voltage difference as VAB as extending between point A and point B. So VAB, this term here, is the voltage difference between this point and that point. Now what does that mean? So VAB, if you think about it intuitively, it's really representing the amount of energy that is gained or lost as a charge moves between A and B. So per unit of charge moving from A to B, okay, VAB tells us the amount of energy that's gained or lost.
And then would it be true then that VBA would be equivalently the amount of energy gained or lost moving from B to A?
Yeah, that's right. So Vivek's point brings up really the most important part, I think, of this slide, which is that voltage is a relative quantity, okay? In other words, we always define a voltage as a difference between 2 points, okay? There's always 2 points associated with it. And absolute voltage is completely meaningless. Now, that might seem weird to you because in common sort of everyday usage, people say things like, the voltage of something is 4 volts. And the reason that happens is part sloppiness, but also part because many times it's very obvious or sort of implicit or understood what one of those 2 terminals might be.
So, as an example, what if we take a battery from a supermarket and I buy a 1.5 volt battery? What does that mean?
Yeah, so what they're saying there is that the voltage difference between the positive and negative terminal is, say, 1.5 volts. And so that's a good example of what I was just talking about. So if we take a charge Q, and remember Q can have positive or negative sign, and it has a certain magnitude, and I take this charge and I move it from point A to point B, the energy required to do this is that Q times the difference, the voltage difference we were just talking about, VAB. So it's Q times VAB. And the thing to understand here is that if you get a positive value when you do this, energy has been lost by the charge. And we're going to see this in a minute when we discuss the passive sign convention. Okay? Conversely, if you get a negative number when you do this, energy has been gained by the charge. And so think about that, how you might sort of intuitively think about how that could happen for charge. Maybe think about it as walking uphill or walking downhill if you were the charge. Okay?
Now that Michelle has introduced the basic idea of voltage, we can now talk about the equivalence. You'll remember in the last section and also with the demo that we did, we talked about the equivalence of directionality and current signs. We see similar behavior for voltages. Remember, as Michelle just pointed out, a voltage is a relative term. So let's consider a circuit on the left where I have 2 terminals A and B, and in this case VAB is 12 volts because A is 12 volts positive of B. If I have another circuit shown on the right, and again I'm going to define VAB, but now I'm going to define it between B and A. So really I'm going to be talking about VBA, and I'll say that's minus 12 volts. Well, in this case, VAB is 12 volts on the left, and on the right, VBA is minus 12 volts. Those are identical. So the reason for that identical nature is, of course, that it's all relative. In the left-hand case, I'm defining A relative to B, and in the right-hand case, I'm defining B relative to A.
So one way to think about this is think about a fictitious, pretend there was a fictitious single voltage called VA, and this bottom term was written as VA minus VB, and on the right side we had VB minus VA with a negative sign in front of the difference. You obviously can see that those things would be the same. It's really where it comes from. Okay, so now let's talk about what ground means from the perspective of this course and what a reference node is. So here's a little circuit, and you don't have to know really what anything does in this circuit at the moment, or even the official sort of definitions of nodes and branches, which we'll get to. But the important thing is, notice I've got a power supply here, and I've got some components, they're resistors, and they're connected by wires, and there's points where these wires sort of intersect and come together, and we'll call these nodes. So notice there's a node right here where these kind of come together. These are all at the same potential. And there's a node, and here's another one at the bottom. Okay, so this is a very simple circuit that we'll very quickly learn how to examine. So it's very important that when you start to solve these things, for many of the techniques we're going to teach you, that you choose a reference point for potential. In fact, it's needed to define anything about potentials. So I'm going to pick some place on this circuit. Now I want to point out two things. The first thing is that you can pick any reference potential you want. Any of these nodes can become the reference point for your circuit. And when you solve it, if you're solving the same circuit, you'll end up with the same answer as someone who put the reference point somewhere else. These things are all consistent. Now, the second thing I want to point out is very often there's an easy place to sort of put it. This is almost a practical tip. And by looking at this, for reasons we'll explain later, I feel pretty comfortable that I want to put my voltage reference down here. Okay?
Is the reason you put it there because it's on the negative end of that battery?
Yeah, that's exactly right. You're sort of jumping ahead of me. So we'll go through this later on, but that's exactly right. I see this battery. I see that this is a negative terminal, and you'll find it very intuitive to put the reference point here to correspond with the terminal of this one supply.
And the reason to do that, by the way, is just as we were talking about earlier, Michel told you that when we get a 1.5 volt battery from the store, it's the voltage of the positive end of the battery relative to the negative. So by defining the voltage reference as the negative end of the battery in this circuit, again, everything just becomes easier to deal with mathematically.
Absolutely. And so for our, for solving these problems, what we're going to do is we're going to call that reference node 0, ground. We're going to call it ground, and we're going to say it's got a potential of 0. That's arbitrary, okay? We're basically just assigning it. Because everything's a difference, we might as well make our lives easier, and we're going to assign one of the nodes to have a 0, and everything else will sort of build on that. You'll see how that works, I think, pretty easily once we start doing problems, okay? And we'll call that ground, and this is a symbol for ground. It's an old symbol intended to represent a wire being sort of plugged into the ground. Okay? Now, all of the potentials, once we do this, all of these potentials are implicitly relative to ground. So what I'm saying is if I drew a V1 here, this is node 1, so I've decided to call this voltage V1. Let's say I called this node 0. This is my reference node. What I really mean is this is V1, 0. Remember we talked about voltages all being differences, right? Relative. So when I say what is V1 and my friend says V1 is 4 volts, what I mean exactly is that the voltage difference between this point here and this point there is 4 volts. Likewise, if my friend says, oh, I solved the problem and V2 is 9.5 volts, what they mean is that the voltage difference between node 2 and my reference node is that 9.4 volts. It's always relative. The differences never go away. It's just that they become implicit in the way we describe the circuit.
So at this point, we've been talking about voltages and currents. I'm sure a question that's popped into your mind is, how do we measure those? Well, there are two devices that we primarily use for these measurements. We use a voltmeter to measure voltage, and we use an ammeter to measure current. So let me explain that in a little bit more detail. A voltmeter is a device that we use to measure voltage. And so in this schematic, you see I've got a voltmeter, and I'm measuring the voltage between points 1 and 2, so between my node 1 and my node 2. Now, the way we do that is we take the two terminals of the voltmeter and we hold it across the points that we're trying to measure the voltage between. And in an ideal world, you don't want that voltmeter to perturb the circuit. So in an ideal world, a voltmeter measures the voltage without drawing any current, so it doesn't perturb the circuit. And then correspondingly, to measure current, we insert an ammeter in series. We'll explain what that means later, but it means it's in line with the current that you're trying to measure, and so it'll measure the current going through it, and ideally it won't drop any voltage across it. So these are the devices that we use for doing our measurements. By the way, in the demo, you saw me using a multimeter already when I was using that to measure current.
So let me make sure I get this. So in this ammeter you've got shown here, current that would normally flow around the circuit from, say, node 2 and around this back to the negative terminal of the battery is going to flow through there anyway, but the ammeter won't cause any additional voltage difference.
That's correct, because remember, the current goes through my circuit, and then now I've inserted that ammeter in there. The current goes through the ammeter and comes all the way around, and because the ammeter doesn't perturb the circuit, as far as the circuit is concerned, the ammeter is basically not there.
So So if the ammeter, if I didn't have the ammeter here, I would have had this node here connected to that one. It would just have been a wire.
Correct.
Got it. Okay, that makes sense to me. All right, let's talk about open circuits and short circuits. These are terms you hear a lot. Oh, that's open, that's short. And so it's good to give you an intuitive grasp and also a definition of what exactly we mean. Okay? So an open circuit is just something where no current can flow down that path. So look at this, very simple. Just imagine there's literally a wire and it ends, and there's another wire that comes out of this point and it ends, and they're not connected by any metal or anything else in here, right? Pretend there was vacuum, if you will. And so no current can flow from 1 to 2. That's an open circuit. Okay, and I'll come back to that in a minute. When we start doing resistance more formally, you'll see that this essentially means that the resistance between here is infinite. Right? The resistance to current flow is infinite.
So going back to the voltmeter case, does that mean that a voltmeter essentially in an ideal world is like an open circuit?
Yeah, exactly. That's
because
exactly
it doesn't
right.
draw any current, right?
That's exactly right. A short circuit basically allows any kind of current, as much current as can go through there, depending on the dictates of the circuit, but no voltage is dropped across here. So this basically is just a perfect wire if you think about a short circuit. It completely and ideally connects this node to that node. And we'll see repercussions of this later when we do circuit analysis, but it's essentially the dual of the open circuit. In voltage, this is the dual in current. And again, when we start doing resistances, you'll see that what this really is there's zero resistance to current flow. It's a perfect short circuit. And the ammeter of the last slide looks like a short circuit.
Okay. So at this point, you've learned a little bit about voltage and current, and in fact, we've learned about the energy that's gained and lost by a charge that moves. So we can now introduce a concept called passive sign convention. And the passive sign convention is used to define whether a black box device in question is generating power within it or is actually using power or consuming power. Let's consider a black box device called device, and it has a current flowing into it from the left side and exiting it on the right side. If the current flows in on the left and comes out on the right, and then if we were to somehow measure the voltage across that device and we found it was positive on the left and negative on the right, that would mean that power is being delivered to the device. So the device would actually be consuming power. If, on the other hand, we had current going into the device, but we found that the voltage on the left side was negative and the right side was positive, that would actually mean that the device was supplying power. The classic example, by the way, for that would be a battery. A battery would supply power because current will actually come out of the positive node and come around back into the negative node.
When you say current, you mean positive current.
That's correct. I'm referring to positive current here. So therefore, when we multiply them together, if P, which is the multiple of V and I, is positive, that means it's consuming power. If P is meaning the multiple of V and I is negative, it's delivering power.
Sounds good. So let's do some examples. So one example. So let's say I've got this circuit, and I don't know what's in this box. We're going to call it device 1. That's what we mean by black box. It's something we don't really know what's in there. And I'm going to connect it to a 12-volt battery as shown. Here's the positive terminal and negative terminal. Okay? And what I find, right, is that I have an 18-volt drop from this positive to this negative terminal, and I have a 6-volt drop from this positive to this negative terminal. Or you can think about it as a minus 6-volt drop if I had put the positive here and the negative here. Okay? And when I do this, I measure that I've got 3 amps of positive current going around clockwise in the direction of this arrow. So now before I show you what the results tell us, notice that this blue arrow, the tip of it, comes in, right? This is the same current on the left side here. It's coming in from left to right, so the tip of this arrow would be coming into the positive, and the tip of this arrow is coming into the negative for this device. Okay? So following that, P is greater than 0 for this device, right? So I've got a positive 3, it's coming in to the positive terminal, 3 times 18, that gives me a positive number, okay? Conversely, for the second device, I've got this 3 amps coming into here, it's coming into the negative. You can think about it one of two ways. A 3 amp current going from left to right, as this arrow is shown, is equivalent through a minus 3 amp current going the other way, going up the circuit, so it would be coming up to the positive terminal. and then I'd get a negative number when I multiplied it. Or I can do what I did a moment ago, is just to say that this is the same, this voltage is the same as putting a plus here and a minus there and minus 6 volts. And so 3 times minus 6 again gives me a negative number.
So just as let's do a quick test. We'll take a 30-second break. What do you think the battery is doing? Do you think the battery is consuming power or delivering power?
I'll give you a hint. Map this back to the battery using the passive sign convention of the last slide.
So remember that what we have is we have an arrow coming out of the positive end now, which means, Michelle?
Which means we did promise them like 10 seconds of silence. That's good enough, I think.
And the answer is?
I think that battery is supplying power.
That's correct.
All right, guys, and let's move on.
So we're finally now at a point where we can start talking about some actual sources. And some of these sources that we're going to talk about won't make a huge amount of sense to you yet, but once we put them into circuits, you'll see what they mean. The first source that I'm going to talk about is the ideal voltage source. And an ideal voltage source is something that is intuitively very obvious to most of you. We often treat batteries as ideal voltage sources. In other words, we assume that they provide a known voltage, for example, the 1.5 volt battery that we talked about earlier.
But, so what you're saying, maybe I'm getting ahead here, but you're saying that this source is going to provide whatever the voltage is defined as, say, this Vs. It's going to define it independent of whatever current has to run through it, right?
In an ideal world,
In an
yes.
ideal world.
In an ideal world, yes. Basically, what we get to assume with an ideal voltage source, that it's going to provide the voltage we set it for, no matter what. No matter how we use it, we're going to get that voltage out of it. We correspondingly have ideal current sources. And these are sources that will provide a specified current, in this case IS, no matter how we use it. And so those are called ideal current sources. Now, in reality, our sources tend not to be ideal. So you remember that battery I talked about? And I said in an ideal world we assume the battery provides 1.5 volts. Well, in reality, most batteries, their voltage drops as you pull more and more current out of them. And the reason is that a battery is really an ideal voltage source with a series resistor. Now, you haven't learned this yet in this module, but you know hopefully from your high school physics about something called Ohm's law, which relates current flow through a resistor to what happens. And in fact, when we flow in an ideal system, we have a voltage source, but in a real system, we have a resistor next to it, and that drops the voltage when we pull current. Correspondingly, we also have realistic current sources, and for reasons that we'll get to later, we model those as an ideal current source with a resistor in parallel.
So let me try to make sense of this. All right. So you're telling me that for an ideal voltage source, the voltage between this point here at the bottom, say, and the voltage on the top, so the voltage difference between the positive and the negative is always fixed at whatever that voltage source value is, no matter what, right?
Correct.
And the same for the current. The current going through this branch from the bottom to the top is always going to be IS. But what you're saying here is that the voltage between, say, the difference between this point and this point isn't always going to be Vs. It's really going to be Vs minus whatever the voltage drop is around the resistor.
That's correct.
And so essentially, depending on what we connect it to, we're going to get a slightly different voltage here. And so this is sort of, the actual voltage here is responsive to what we connect it to.
That's right.
It
Depends on how we use it.
I got it. All right, this is going to be cool. This is interesting. All right. All right. Well, I think we're going to wrap up here, and I just want to point out to you what are called dependent sources. We're going to use these a lot in class, and they might look a little scary at first, but in fact, they're really, really not, I promise you. So we draw them like diamonds. You saw that in the last slide, the independent sources were all circles. And so all this is saying is that, let's take the one on the top left. All that's saying is that the voltage difference between the positive and the negative node, called Vs, is linearly proportional. So this alpha is just some proportionality constant that somebody dreamed up or is a property of that device. We'll see it. It'll depend on the device. So the voltage is linear proportional to some other voltage in the circuit, this Vx. And notice this Vx isn't drawn anywhere on here. It could be anywhere in the circuit. In fact, it could be anything. I could come up with any mathematical formula that says the voltage difference between some other 2 points. Let me give you a concrete example. Let's say this sits in a circuit, this voltage-controlled voltage source, and somewhere else in the circuit there's a resistor, and the voltage across that resistor is Vx. What this is telling me is that the voltage from positive to negative of this source is dependent on the voltage on that resistor times some proportionality constant. Okay?
Before you get too confused by this, don't worry about the details. We will show you more about how we implement these later and why they're important later. For now, just be aware that we can build circuits that are essentially voltage sources where the voltage they produce depends on the voltage somewhere else. And that's called a voltage-controlled voltage source.
Yeah, got it. And we're going to do a lot of these, so don't worry. We're going to have lots of problems, and you'll see they're actually pretty simple. Now, just, you know, this top left example is sort of a voltage source that depends on another voltage. But we've got both voltage and current, so there's 2 times 2 combinations, that's 4. So in other words, I can have a current source that's defined by a voltage somewhere. That's the top right example. I could have a current source that's defined by a current somewhere. That's the bottom right example. And I could have a voltage source that's defined by a current somewhere. That's the bottom left example. And we can mix and match and make all sorts of stuff. Okay, so I think we're going to wrap up here, and we'll see you very soon.